बताना। गुड इवनिंग, नमस्कार, कैसे हैं आप सभी लोग? उम्मीद है मेरी आवाज और मेरा वीडियो आप तक पहुंच रहा होगा। सो आई वेलकम यू ऑल ऑन दिस सेशन। इन दिस सेशन आप गेट थ्रू क्वेश्चंस और हम लोग इलेक्ट्रॉनिक डिवाइसेस एंड सर्किट्स के कुछ क्वेश्चंस का डिस्कशन करेंगे। छोटा सा सेशन रखेंगे, बहुत लंबा सेशन करने का इरादा नहीं है, बट वी वुड बी डिस्कसिंग फ्यू क्वेश्चंस एग्जैक्टली ऑन द सेम पैटर्न ऑफ द गेट एग्जामिनेशन। जिस तरह से गेट में क्वेश्चंस आते हैं उसी तरह के कुछ क्वेश्चंस डिस्कस करेंगे। थ्योरी डिस्कस करने का कोई इरादा नहीं है, डायरेक्टली क्वेश्चन सॉल्व करेंगे। थ्योरी के बहुत सारे सेशन मैं अलग से ले चुका हूं और ऑनलाइन भी बहुत सारे सेशन पड़े हुए हैं, बाकी क्लास में तो आपको डिटेल में पढ़ा ही चुका हूं। तो चलिए क्वेश्चन करते हैं। मैंने कोई ऑर्डर नहीं रखा है। यूजुअली ज़्यादातर क्लासेस जब मैं करता हूं तो जो सीक्वेंस क्लास में फॉलो करता हूं वही सीक्वेंस है ऑनलाइन सेशंस में भी, क्वेश्चंस में भी करते हैं, जैसे सेमीकंडक्टर फिजिक्स के, फिर जंक्शंस के, फिर मॉस कैपेसिटर, मॉसफेट, बीजेटी, लाइक दैट। बट इस बार मैंने कोई सीक्वेंस नहीं रखा है, जम्बल्ड किए हैं। जैसे एग्जाम में कोई सीक्वेंस नहीं होता है तो कोई भी क्वेश्चन, किसी भी टॉपिक का क्वेश्चन कहीं पर भी जम्बल करके एंड करने का प्रयास किया जा रहा है। पहला क्वेश्चन यही लेते हैं, कंसीडर इंट्रिंसिक जर्मेनियम एट रूम टेम्परेचर। सो क्या दिया हुआ है? रूम टेम्परेचर, दैट इज 300 केल्विन। सबसे पहले देखते चलिए क्या क्या इंफॉर्मेशन क्वेश्चन में है। ठीक, 300 केल्विन विद एनर्जी बैंड गैप Eg। 300 केल्विन पर इसका जो बैंड गैप है दैट इज 0.785 इलेक्ट्रॉन वोल्ट। थोड़ा सा मिसिंग है इंफॉर्मेशन, मुझसे लिखने में कुछ मिस्टेक हो गई है। दिस इज द एनर्जी बैंड गैप एट 0 केल्विन। दिस इज यहां पर क्योंकि मैं क्वेश्चन थोड़ा जल्दी जल्दी में फ्रेम किया बनाया, तो ये लिखेंगे आप एट 0 केल्विन। ठीक, सो दिस इज बेसिकली योर Eg नॉट गिवन, करेक्ट कर लीजिएगा। Percentage change in conductivity per degree rise in temperature is neglect change of mobility due to temperature. This line is very important. Although you know that when you are at the room temperature, then mobility is mainly limited by the lattice scattering, and if mobility is limited by lattice scattering, then with increase in temperature, lattice vibration increases and mobility will decrease. So near about room temperature, if you are operating any device, semiconductor device, yeah, you are working on a semiconductor material, then with increase in temperature, mobility should decrease. बट इन द क्वेश्चन ही इज सेइंग दैट कि नेग्लेक्ट चेंज इन मोबिलिटी, मोबिलिटी में जो चेंज हो रहा है वो कंसीडर नहीं करना है। तो ये इंट्रिंसिक सेमीकंडक्टर की पहले कंडक्टिविटी देखते हैं। व्हाट इज द कंडक्टिविटी ऑफ इंट्रिंसिक सेमीकंडक्टर? सिग्मा आई, this is the conductivity of intrinsic semiconductor. So we can write this sigma I like this: sigma I is equal to Ni Q mu n plus mu p. For us, mu n and mu p are constant. And Q is what? The magnitude of electronic charge, that is 1.6 into 10 raised power minus 19. This is also constant. So this entire part is constant. Any change in intrinsic carrier concentration will change the mobility, conductivity of this particular material. So let us try to understand how the intrinsic carrier concentration is changing. So we know that intrinsic carrier concentration Ni, it is like this: under root A naught T to the power 3 by 2 E to the power minus Eg naught upon 2 kT. This is the formula for the intrinsic carrier concentration. Here A naught is material constant, Eg naught is energy band gap at 0 Kelvin, K is Boltzmann constant, T is temperature. These all things we know very well. So let us put this value here. यहाँ पर इस value को put करते हैं. So sigma I, and we put this Ni, that is root A naught, and this is T to the power 3 by 2, and this is E to the power minus Eg naught upon 2 kT into this Q into this mu n plus mu p, mu n plus mu p, right? Let's remove this line, को हटा देते हैं। This is intrinsic carrier concentration. ठीक, now let's collect the constants, एक साथ कर लेते हैं। तो sigma I root A naught, it is a constant, Q is a constant, mu n plus mu p according to the question they are the constant, and then T to the power 3 by 2 into E to the power minus Eg naught upon 2 kT, right? Dear friends, let us write this as a constant C1. इस पूरे पार्ट को कुछ एक नया नाम दे देते थे, कांस्टेंट का C1 मान लेते हैं, because this all is independent of temperature. So sigma I is equal to C1 T to the power 3 by 2 and E to the power minus Eg naught upon 2 kT. I want to calculate the change in conductivity with respect to the temperature. So if we want to see the change with respect to temperature, then we should differentiate this with respect to the temperature. But if you differentiate this directly with respect to temperature, the expression is going to be complex. So we will use little bit mathematics. थोड़ा सा हम मैथमेटिकल माइंडसेट अपना यूज करेंगे. हम क्या कर लें, इसका लॉग ले लें, दोनों तरफ का लॉग ले लेंगे तो ये प्रोडक्ट जो है, जो मल्टीप्लिकेशन है, वो एडिशन में कन्वर्ट हो जाएगा और हमारे लिए ये एक्सप्रेशन सॉल्व करना इजी हो जाएगा. सो टेकिंग लॉग ऑफ बोथ साइड्स वी विल हैव लॉग सिग्मा आई इज इक्वल टू लॉग C1. अब देखिए ये A इंटू बी इंटू सी, 3 पार्ट्स में लिख सकते हैं. लॉग A इंटू बी इंटू सी इज इक्वल टू लॉग A प्लस लॉग B प्लस लॉग C. सो आई विल राइट लॉग C1 प्लस log T to the power 3 by 2 plus log this part E to the power minus Eg naught upon 2 kT. If I solve this, it is going to be equal to log sigma I is equal to log C1 and this is plus 3 by 2 log T minus Eg naught upon 2k into 1 upon 2, right? Log e to the power minus this is to minus Eg naught by 2k. Let's differentiate with respect to the temperature. इसे हम टेम्परेचर के रेस्पेक्ट में डिफरेंशिएट करें. So if I differentiate this, log sigma को डिफरेंशिएट करेंगे, so it is 1 upon sigma I. Then sigma I का डिफरेंशिएशन with respect to temperature, this sigma I upon dt is equal to, this is 0, this is 3 by 2 into 1 upon t and then this minus Eg naught upon 2k into minus 1 upon t square. ठीक है, let's simplify this. This portion is nothing but you can write like this, d sigma I upon sigma I upon dt. For 1 degree centigrade change in temperature, this is the change in relative change in conductivity. If you want to calculate it in percentage, just multiply by 100, you will get in percentage. This value is equal to, this is 3 by 2 into 1 upon t, this minus minus plus Eg naught and this 2 I can write it like this, kT into t. Right? Now put all these values are given to us. We have T is 300 Kelvin. So I can put this value like this, 3 by 2 into 300 plus Eg naught is given is 0.785 electron volt upon 2 into this 0.026 electron volt at room temperature. The kT value you know very well, and then T is 300. So this is your change in conductivity for 1 degree centigrade change in temperature. Electron volt will get cancelled out and you solve this, you will get the desired value. So I am going to get something like this, 3 upon 2 multiplied by 300 and this goes at 0.005. This is 0.005 plus this portion, this is 0.785 divided by 2 into 0.026 into 300. This goes at 0.050, 0.0503. You add these two and you will get the 0.005. So this is good as 0.055 per degree centigrade. I want this in percentage, so just multiply by 100. So to get in percentage, just multiply it by 100. इसे 100 से multiply कर दो, so you will get it. Multiply by 100, it will be 5.5% per degree centigrade. So answer for this question is 5.5% per degree centigrade. Let's see what are the options given. 5.56. So nearest option is option C. So right choice for this question is given by option C. Answer for this question is option C. ठीक है. सो इस तरह के क्वेश्चन आपसे पूछे जा सकते हैं. यू नीड टू सॉल्व देम इन दिस वे. इसी तरह से आप सॉल्व करने का प्रयास करिए जैसे मैंने किया है. जो जो इंफॉर्मेशन दी हुई है पहले वो देख लीजिए एंड देन ट्राई टू फिगर आउट कि आपको पता क्या करना है. फिर दी हुई इंफॉर्मेशन और जो चाहिए उसके बीच का गैप क्या है, उस गैप को फिल करने की कोशिश करिए. जो आपने पढ़ा है वहां से चीजें यूज करिए. जहां हो सके सिंप्लीफिकेशन के लिए मैथमेटिक्स का यूज करिए. देन थिंग्स विल बी इजियर फॉर यू. लेट अस मूव ऑन टू द नेक्स्ट क्वेश्चन. अगले क्वेश्चन की तरफ चलते हैं. Next question, very good question. Consider the energy band diagram of a semiconductor where A and B represents the two electrons in the conduction band. This question can be MSQ. You need to check. मैंने बताया नहीं कि ये MCQ है या MSQ है. आप चेक करिए, ठीक, क्योंकि अगर एग्जाम में कभी ओवरलुक भी हो जाए आपसे थ्योरेटिकल क्वेश्चन जब भी है तो देखिए कि कहीं मोर देन वन ऑप्शन तो करेक्ट नहीं है. मित्रों एक चीज आपको याद हो, थोड़ा सा थ्योरी जो मैंने क्लास में पढ़ाया हुआ है एनर्जी बैंड डायग्राम का आपको दिखाना चाहूं तो मैंने आपको क्लास में ये पढ़ाया हुआ है कि लेट अस सपोज दिस इज अ सेमीकंडक्टर मटेरियल. सपोज इट इज एन टाइप सेमीकंडक्टर मटेरियल. आई एम अज्यूमिंग इट कैन बी पी टाइप आल्सो, बट आपने जो क्लास में पढ़ा है उसके सिंक्रोनिजन में चीजें बनी रहें इसलिए मैं इसे एन टाइप मान ले रहा हूं. So let us suppose this is n type semiconductor material and some voltage V naught is applied across it, across the length of this material. This is suppose your x-axis and I am assuming that this point is your x is equal to 0 point and this point is your x is equal to L point, right? I want to draw the band diagram under this applied voltage condition. I have taught you in the class one very important concept. Electric field intensity E can be written as 1 upon Q. This is your electric field intensity. This is what? Electric field intensity. Electric field intensity, right? This is electric field intensity. This electric field intensity can be written as DEC dx. Slope of the conduction band 1 upon Q. Slope of the valence band 1 upon Q, slope of the intrinsic Fermi energy level. 1 upon Q, slope of intrinsic Fermi. इन तीनों में से किसी की भी slope आपको पता हो तो you can calculate the electric field intensity. In other words, I can say that if there is an electric field across the material, then the conduction band and valence band will have certain slope, and that slope can be calculated from this relationship. So let us try to draw here. Here, since you are applying voltage across the length, so voltage per unit length will cause an electric field. So if you draw the band diagram for this, it is going to be slopey. Right, now let us see. In this case here you see, I have told you to draw the band diagram something like this. You draw it like this. Let us suppose potential at this point, this is low potential point, so I am assuming that low potential is 0. If the potential is 0, then what is the energy? Energy is minus Q into phi, conduction band energy of electron, so it is 0. So energy of electron, yani EC for the electron at this point is 0. This is EC, right? Now this line is, this point is representing 0 point. This is representing 0 point, okay? Above this energy will be positive, below this energy would be negative. This point is representing the 0 energy level. Now you see at this point what is happening. This is high potential. So at high potential point, potential is V naught. Whatever is the potential difference, that I am taking as high potential. Now at this point, what is the conduction band energy? That is minus Q into phi. Phi is V naught. So Q V naught. So the energy of the electron at this point is negative, and how much less than the 0? That is Q V naught less than the 0. So here the energy of electron should be like this. Below this negative, and how much below this? Q V naught, right? So now if I have to plot the conduction band under this condition would be like this. This is your EC. I have told you EC, EB and EI are parallel to each other. So once you get the EC, then EI and EB will be the blind follower. So this is EB and then EI would be the blind follower. So this is EI. And what is the EF? If I talk about the EF, it is going to be like this. So this is the EF. This is EF. This is EF. Right? Now you see, what I am trying to tell you, if there is an electric field in the semiconductor, then there must be some slope in the conduction band and valence band. If there is no electric field, then this slope will be what? 0. This slope dEC upon dx is equal to 0. Then what is the electric field? This is 0. And if the electric field is 0, then the electron will have only will not have any additional energy. It is the energy, it is at the 0 energy level. But if there is an electric field, and if you give that electric field, then the electron will have certain higher energy. Whatever is the electric field, उस electric field की energy लेकर के ये EC से above होगा. ठीक है. चलिए इन्हीं concepts का use करके इस question को solve करने की कोशिश करते हैं. Now you see, this is the band diagram. In this band diagram, here the slope is 0. So dEC dx, this is the 0 slope. 0 slope means electric field is 0, and if electric field is 0, then the energy of electron किसके बराबर होगा? सिर्फ इस लेवल के बराबर, EC के बराबर, या यूं कह लें कि 0 एनर्जी का इलेक्ट्रॉन होगा. ठीक है. काइनेटिक एनर्जी ऑफ इलेक्ट्रॉन इज 0, यू कैन से दैट वुड बी द बेटर, क्योंकि यहाँ तो जस्ट फ्री ही हुआ है. अगर उसे मूव करना है तो यू नीड टू गिव सम एनर्जी फ्रॉम द अप्लाइड इलेक्ट्रिक फील्ड, बट देयर इज नो इलेक्ट्रिक फील्ड, सो काइनेटिक एनर्जी ऑफ इलेक्ट्रॉन इज इक्वल टू 0. But here if you go, you see there is a slope. So because of this slope, dEC upon dx is non-zero, so electric field is non-zero, and if electric field is non-zero, then kinetic energy of electron should be non-zero. And that is the reason why electron is represented at some high energy. Here it is represented. This will have some electron energy. Now again in this region, if you go, this is just similar to this region. So here if you see dEC upon dx is equal to 0. So Ke of electron, this is of electron, this is equal to 0. Let us see the options. Options देखने की कोशिश करते हैं. पहला option. In region first and third, electric field is 0. So this is region first, this is region second, this is region third. So in region first and third, electric field is 0, and in region second, non-zero electric field exists. Yes. Here the electric field is 0, here the electric field is 0, but here electric field is non-zero. Here this means electric field is 0 and kinetic energy is 0. In the region third, electric field is 0, and in the region, this is wrong, opposite. Kinetic energy of electron A is 0 and that of electron B is non-zero. Yes. इस इलेक्ट्रॉन की काइनेटिक एनर्जी 0 बिकॉज देयर इज नो इलेक्ट्रिक फील्ड, बट इस इलेक्ट्रॉन के पास कुछ काइनेटिक एनर्जी है. सो दिस इज सी. काइनेटिक एनर्जी ऑफ इलेक्ट्रॉन ए इज नॉन जीरो. दिस इज रॉन्ग. सो ऑप्शन ए एंड सी आर करेक्ट. दिस इज MSQ क्वेश्चन. मल्टीपल ऑप्शंस आर करेक्ट. सो आंसर फॉर दिस क्वेश्चन इज गिवन बाय दिस these two options. इन दोनों ऑप्शन से. सो इस क्वेश्चन को सॉल्व करने के लिए जो रिक्वायर्ड थ्योरी है वो मैंने यहां डिस्कस की है, ये फॉर्मूले, एंड इसके हिसाब से जो इसका आंसर आएगा वो ए और सी आएगा. दीज आर द टू ऑप्शंस वी विल हैव. चलिए आगे चलते हैं. लेट्स गो अहेड. So, are you enjoying? ऐसे ही सिंपल बेसिक कंसेप्ट्स पर गेट में क्वेश्चन पूछे जाते हैं. कोई बहुत अलग से क्वेश्चन नहीं पूछे जाते हैं. आपने अगर कंसेप्चुअली अच्छा पढ़ा हुआ है तो आप सारे क्वेश्चन कर लोगे. So it is a good question, you can do it. नेक्स्ट आगे चलते हैं. An ideal n channel MOSFET has the parameters W. ये MSQ यहाँ लिख दिया है, so more than one options can be correct. ठीक. So an ideal n channel MOSFET has the parameters W 15 micrometer, L 1.5 micrometer, mu1 1350 centimeter square per volt second, T ox. This is oxide thickness basically. Threshold voltage of MOSFET is 0.8 volt. The transistor is operating in the linear region at VDS 1.5 volt. epsilon oxide is 4 epsilon naught. Which of the following options are correct? The value of oxide capacitance. हर एक option को solve करते चलिए. So what is oxide capacitance? Let us try to calculate. So first option is oxide capacitance. मैं option A verify कर रहा हूँ. This is nanofarad per centimeter square, means we want to calculate oxide capacitance per unit area. So it is epsilon oxide, that is permittivity of oxide is 4 epsilon naught. So it is 4 epsilon naught upon T oxide. We need in centimeter per centimeter square, so put all the values in centimeter. 4 into 8.854, you know the value of epsilon naught, into 10 raised power minus 14. This I am putting in farad centimeter. Then this T oxide, this T oxide is oxide level thickness. Oxide layer thickness is given in the question, that is 300 angstrom. Now convert 300 angstrom. 300 angstrom. Angstrom is what? 300 into 10 raised power minus 10 meter. I want this into centimeter. So 300 into 10 raised power minus 8 centimeter. Right? So it is 300 into 10 raised power minus 8. This will come into farad per centimeter square. But I want this in nanofarad because in the question it is in nanofarad. So minus 9 को बाहर करके then simplify करो. So if I simplify this, 4 into 8.854 into 9 यहाँ से ले लीजिए. So 10 raised power minus 5 into 10 raised power minus 9 farad per centimeter square divided by 300 into 10 raised power minus 8. Let's simplify this. आइए इसको simplify करते हैं. When we simplify this, this will come into nanofarad per centimeter square. This part, ठीक, nanofarad per centimeter square. Now solve this part. So if I solve this part, 4 into 8.854 into 10 raised power minus 5, and this divided by 300 into 10 raised power minus 8, and that is going 118.05. This is 118.05 nanofarad per centimeter square. 118. ठीक. Once again check the calculations because sometimes I do calculation mistake. Those who have attended my class, they know very well. मैं कैलकुलेशंस की कोई जिम्मेदारी नहीं लेता, किसी भी तरह की नैतिक जिम्मेदारी नहीं लेता, तो आपको कैलकुलेशन चेक करना पड़ेगा. ठीक. So it is 118. So it is roughly 118, but in the question it is given 11.8. So this option cannot be correct. This is wrong option. ठीक है. Now two options are related with GM. Three, all of these three are related with GM, and GM in linear region. He is asking what? Linear region. अब देखिए transistor is operating in linear region. So first of all, try to write the equation in linear region. Try to write the equation in linear region for enhancement MOSFET. So linear region में what you will have? Linear region. In the linear region, you see, when you get the linear region, the condition you know, drain to source voltage must be less than or equal to, not equal, basically it should be less than BGS minus VTH. Then you will have linear region. This is linear region. And for the saturation region, this voltage should be greater than or equal to. In the linear region, the drain current ID, yeah, drain to source current IDs, whatever you want to write, that is mu n C ox W by L into this VGS minus VTH into VDS minus VDS square by. Let's simplify this. If I simplify this, it is going to be, मुझे GM चाहिए, transconductance. Transconductance is what? Differentiation of this with respect to BGS, keeping VDS as constant. So del ID del VGS कब? When BDS is constant. VDS is constant. This is the definition for GM, transconductance, right? Now if you differentiate this mu n Cox W by L and the differentiation of this term BGS के रेस्पेक्ट में कर रहे हैं 1 minus 0 into VDS minus this 0, right? So our GM equation will come something like this. GM is equal to GM is mu n Cox W by L and into BDS. One moment, one conclusion, GM is directly proportional to BDS. In the linear region, if you increase drain to source voltage, GM will increase. So you see one of the options here. The value is independent, the value of GM is independent of BDS. Wrong. It is a function of BDS because everything he is saying in the linear region, and in linear region you derive that it is a function of BDS, it will depend. The value of GM is independent to BGS. Yes, in the linear region, my dear friend, if you see, there is no expression for BGS. It is depending upon BDS, but it is independent of BGS. So this expression is telling you that option D is right. Stick. Now I have to check the value for the GM. So let's calculate the value for GM. Put all these values and try to calculate. So what is the GM? GM is mu n, mobility of electrons is given to you. Mobility of electrons is something like this. GM is given in the question, that is 1350 centimeter square per volt second. 1350, सब कुछ सेंटीमीटर में रखना because ये सेंटीमीटर में. Then C oxide, nanofarad per centimeter square. So nano के साथ put कर दीजिए. So it will be 118.05 into 10 raised power minus 9. 118.05 into 10 raised power minus 9. Farad per centimeter square cancel हो जाएगा. Into W by L, same unit में रखिए, dimension less हो जाएगा. So W by L is 15 by 1.5. So 15 by 1.5. 15 by 1.5 into BDS. What is the BDS given? BDS is given as 1.5. So it is 1.5. This is ampere per volt. Let's simplify this and try to get the answer for this question. So इसको simplify करिए. 1350 multiplied by 118.05 into 10 to the power minus 9 into 15 by 1.5. So it is 150 by 15, that is 10 into 1.5. 1.55 कट जाएगा, so 15 हो जाएगा. Right is right. So it is, in the options he is saying in milliampere, I think milliampere per volt, yeah, millisiemens. Millisiemens. So multiply by 1000. This comes out 2.39 millisiemens, so it is correct. It is 2.39 millisiemens. 2.39 millisiemens, right? Ampere per volt is nothing but Siemens. So this option is also correct. Which one is correct? B is correct. So right answer for this question is B and C. इसके लिए जो आंसर हो जाएगा वो क्या होगा? B और C हो जाएगा. The answer for this question is B and C. Right? इसके लिए सही जवाब होगा B and C. Do this. Right? Good question. Very good question. Not only good, it's very good question. अगले क्वेश्चन की तरफ चलते हैं. क्विकली देख लीजिए. Then we'll move to next question. आइए नेक्स्ट, अगले क्वेश्चन पर चलो. In an application, a sample of germanium is doped with donors and acceptors. You see, you have single sample of germanium and you are adding both acceptor and donor. Recall in the class I tell you one very important thing. If it is a single sample and you are adding both types of impurities in this sample, you are adding donor as well as acceptor. It means it is the case of compensated semiconductor. What is the definition of compensated semiconductor? Compensated semiconductor की क्या definition मैंने आपको पढ़ाया है? मैंने आपको यही पढ़ाया कि अगर एक ही सेमीकंडक्टर में दोनों तरह की इंप्योरिटी सेम रीजन में ऐड कर रहे हैं तो जो रिजल्टिंग सेमीकंडक्टर है वो कंपनसेटेड सेमीकंडक्टर कहलाएगा. A compensated semiconductor is the semiconductor which contains both types of impurities, donors and acceptors, within the same region. Right? So this question is from the compensated semiconductor sample. So let us try to see first. What is the amount of donor? This is the amount of donor. So ND is how much? It is 10 to the power 12 per centimeter cube. This is ND. And then if you talk about this, this is acceptor. The acceptor NE is 5 into 10 to the power 10 per centimeter cube. Now there arises three cases. If donor concentration is greater than acceptor concentration, then it is compensated N-type semiconductor. If donor concentration is less than the acceptor concentration, then it is compensated P-type semiconductor. And if donor and acceptor concentrations are equal, then it is fully compensated semiconductor with intrinsic like characteristics. You cannot say it intrinsic, क्योंकि intrinsic की definition मैंने आपको क्या लिखाई है? A semiconductor in its purest form is known as intrinsic semiconductor. A semiconductor sample is not said to be intrinsic unless impurity content is less than 1 part among the 100 million parts of the semiconductor. So यदि आपने impurity add कर दिया है and you are adding impurity which is greater than 1 part in 100 million parts of the semiconductor, then it cannot be intrinsic. So here if donor and acceptor concentrations are equal and they are in the large amount, then semiconductor will not remain intrinsic. It will be doped semiconductor. But since these impurities are fully compensating each other, so the behavior of the semiconductor from carrier concentration point of view would be like the intrinsic semiconductor, but it cannot be said as intrinsic. So that's why I safely say that if Na is equal to Nd, then completely compensated or fully compensated semiconductor with intrinsic like characteristics. Right? So what my point here is, we will have three cases. Let us first check in which case this question lies. So in this question, if you see donor concentration, how will you compare this? Forget about this unitary digit, compare the powers. So if you compare the powers, it is 10 to the power 12 and it is 10 to the power 10. It means donor concentration is greater than the acceptor concentration. So here we are having Nd greater than Na. It means it is compensated N-type semiconductor. Compensated N-type semiconductor. To solve such kind of questions, you have to do first of all this thing. So it is compensated N-type semiconductor. Now you try to calculate Nd minus Na. इस question के लिए क्या calculate करेंगे आप? Nd minus Na. So if I calculate Nd minus Na, it goes like 100 into 10 to the power 10 minus 5 into 10 to the power 10. This 10 to the power 12 I have written like this. So I can write is 95 into 10 to the power 10, and that can be written as 9.5 into 10 to the power 11 per centimeter cube. This is the effective donor concentration which is making it compensated N-type semiconductor. किसी भी कंपनसेटेड सेमीकंडक्टर के लिए इतना तो आप करो ही, ठीक. अब आगे चलते हैं. At the temperature of this sample, the resistivity of pure germanium is this. So what is the resistivity of pure germanium? This is equal to 50 ohm centimeter. This is the resistivity of pure germanium. If an electric field of 5 volt per centimeter, electric field is 5 volt per centimeter, is applied the sample, then the conduction current density, you need to calculate J, that is the conduction current density. Given mobility of electrons are 3800 and mobility of holes is 1800. So you have been given two more information, that is mu n is how much? 3800 centimeter square volt second, and mu p is that is how much? 1800 centimeter square volt second. My dear friend, what I want to calculate conduction current density. So let us start from here. जब कुछ ना समझ में आए तो यहीं से शुरू करो कि निकालना क्या है. So हमें निकालना है conduction current density. From basic formula it is sigma into E. यही पढ़ा मैंने, ओम्स लॉ, राइट? ये आपको क्लास में पढ़ाया हुआ है. So J is equal to sigma into E. Sigma is conductivity of the semiconductor. Here the semiconductor is what? It is n-type semiconductor. So this sigma is basically the conductivity of n-type semiconductor. Conductivity of n-type semiconductor nq mu n. No, this is only if electron concentration is very greater than the hole concentration. If electron concentration and hole concentration are comparable, then you would be writing nq mu n pq mu p. I don't know as of now. Electron concentration is equal to hole concentration. Yeah, it is greater than hole concentration, or it is very much greater than hole concentration. So first of all, I need to calculate electron and hole concentration, then only I can comment what is the conductivity of this semiconductor. अगर आपने गेट के क्वेश्चन में डायरेक्टली ये लगा दिया NQ mu n, आप एक हिडन एजम्पशन ले रहे हो, और वो हिडन एजम्पशन ले रहे हो कि द डोनर कंसंट्रेशन ND minus NA is far greater than NI. This is valid only if this condition is followed. I don't know here as of now whether this condition is followed or not. वैसे भी मैं अगर कोई क्वेश्चन डिस्कस करने के लिए आ रहा हूं तो हालांकि बहुत सारे क्वेश्चन गेट में है जो डायरेक्टली इस पे हो जाएंगे, ठीक, बट इस क्वेश्चन में नहीं. तो आपको कंसेप्ट को समझना है कि कब कौन सा फार्मूला लगाएंगे. तो ये फार्मूला हम तब लगाते हैं जब डोपिंग कंसंट्रेशन इज ग्रेटर एज कंपैरिजन टू द इंट्रिंसिक कैरियर कंसंट्रेशन, एंड हेंस मेजॉरिटी कैरियर कंसंट्रेशन इज वे अहेड या वेरी हाई एज कंपैरिजन टू द माइनॉरिटी कैरियर कंसंट्रेशन. Here I cannot conclude as of now कि n is greater than or equal to what is the condition on n, that I cannot conclude. Although since it is n type, so n will be greater than the p, but how much greater? Whether I can apply this condition or not, right? So I need to calculate electron and hole concentrations in order to understand whether we can apply this formula or not. To calculate the electron concentration in a compensated n-type semiconductor, what formula I told you? I told you n is equal to ND minus NA by 2 plus under root ND minus NA by 2 का square plus NI square. My dear friend, I used to write it like this, but this is valid only if ND minus NA is far greater than NI. Only if this condition is followed, then only I can neglect this and n will become equal to ND minus NA. But I cannot use here. मुझे NI पता ही नहीं है. So first of all, I try to calculate NI, then I can calculate the electron concentration. Yeah, I can approximate the electron concentration. So how can I calculate NI? To calculate NI, this information is given. What is given? I have been given rho I. Rho I is 1 upon sigma I, which is equal to 1 upon NIQ mu n plus mu p, right? So from here, if I want to calculate NI, this will go as 1 upon rho I q and mu n plus mu p. Put all these values and solve it. So if I put all these values and solve it, 1 upon rho I is given in the question. How much its value? Its value is 50 ohm centimeter. 50 into 1.6 into 10 raised power minus 19 into mu n plus mu p. What is mu n plus mu p? 3800 plus 1800. So we will have 3800 plus 1800. If I solve this, I'll get intrinsic carrier concentration in per centimeter cube. So 50 into 1.6 into 10 raised power minus 19 into 3800 plus 1800, and reciprocal of this, it goes 2.23 into 10 to the power 13. 2.23 into 10 to the power 13 per centimeter cube. 2.23 into 10 to the power 13 per centimeter cube. Now you see, my dear friend, What is Nd minus Ne? Nd minus Ne is in the range of 10 to the power 11, basically 10 to the power 12. Here 9.5 is almost 10, so 10 to the power 12, and it is 10 to the power 13. Doping is Nd minus Na is not greater than Ni, rather it is less comparable. So you cannot do this approximation. आप ये approximation तो बिल्कुल भी नहीं कर सकते हो कि आप इसको neglect कर दो. You have to consider this. So put all these values and solve electron concentration. So if I put this Nd minus Na, we are having 9.5 into 10 to the power 11 by 2 plus under root this 9.5 into 10 to the power 11 by 2 ka square plus the Ni value which we have calculated just now. We have calculated 2.23 into 10 to the power 13. So 2.23 into 10 to the power 13 square. Let's solve this. Let's solve this. So if I solve this, it goes like 9.5 into 10 to the power 11 and this divided by 2 and square plus 2.23 into 10 to the power 13 का square and इस पूरे का square root, and this is 2.23 into 10 to the power 13. You see, this part has become negligible and it is almost just like intrinsic. So this n is approximately equal to 2.23 into 10 to the power 13 per centimeter cube. This is electron concentration, right? Now if you have calculated electron concentration, then you can calculate hole concentration from mass action law. What does mass action law says? N into P is equal to Ni square. So I can write P is equal to Ni square upon N. So this goes as here I have done some approximations, I think, but answer would be almost same. So this P will also be remain same, 2.23 into 10 to the power 13 per centimeter, right? Now sigma will, then the conductivity will remain same. If it is just like intrinsic, then even if you put the values, the conductivity will remain same. The conductivity is the same as we have got there, that is 1 upon 50, and that is 0.02, right? It is just behaving like intrinsic, although you are trying to dope it, but even after doping you see the intrinsic carrier concentration के बराबर ही आ रहा है. So the conductivity would be the reciprocal of this. So if I solve, then conductivity is nothing but sigma I is equal to 1 upon rho I, and that is equal to 1 upon 50. And if I go this 1 upon 50, so this is 1 upon 50, and that's 0.02, and J is equal to sigma into E, so that is 0.02 into E is 5, I think. E is 5. 5. So it is ampere per centimeter square में आ जाएगा, so multiplied by 5, and that is 0.1 ampere per centimeter square. आंसर हमें किस में बताना है? मिली एम्पियर में, आई थिंक. Yes, so multiply it by 1000, so it will become 100 milliampere per centimeter. I have done a little bit approximation, so maybe sometimes in class I may not have done approximation, then the answer would have been 100.6 milliampere per centimeter square. But ऐसे क्वेश्चन में इतनी रेंज देगा कि अगर 100 है, so 99 to 101 या 99 into 102, something like that kind of range आपको मिलेगी. So it would be correct. This much of the approximation you can do in the question, and then you can solve like this, right? So please go ahead and solve it. If you want, you यहाँ जो मैंने approximation data में किया वो मत करिए, लास्ट में पूरा ही लिख लीजिए. So this is your question regarding with the conductivity. So at the end मैंने कहानी उसने खूब दिया है, but यहीं से भी आप देख सकते थे क्योंकि डोपिंग इज लेस देन द इंट्रिंसिक कैरियर कंसंट्रेशन. सो मेनली जो कैरियर होंगे ये पार्ट नेग्लेक्ट हो जाएगा, ये पार्ट नेग्लेक्ट हो जाएगा, इसी के बराबर आएंगे. और जब इलेक्ट्रॉन कंसंट्रेशन सेम है तो होल कंसंट्रेशन भी सेम रहेगी, इंट्रिंसिक जैसा बिहेव करेगा. आइए इस क्वेश्चन को करते हैं, वेरी गुड क्वेश्चन, राइट। कुछ एक क्लास में कई बार वर्कबुक में करा देता हूँ, कई बार छूट जाता है, तो मैंने सोचा आज इसको यहाँ कर लेते हैं, ठीक है। सो वी बी डूइंग दिस क्वेश्चन आल्सो हियर। An abrupt p-n junction located at x is equal to 0 is uniformly doped on both sides of p and n sides. The width of the depletion region is W and the electric field variation in the x direction is Ex. Which of the following figures represents the electric field profile near the p-n junction? क्वेश्चन में p-n junction लिख रहा है, बट एग्जाम में हमेशा आंखें खुली रखनी चाहिए। चारों ऑप्शन में देखें, N P N P N P N P. So basically it is NP junction, and he is asking what is the electric field profile for the NP junction, right? So let's try to calculate the electric field profile for NP junction. This is your N side and this is your P side. It is uniformly doped, so junction is formed here. This point is your x is equal to 0 point where junction is formed, and this is your x-axis, right? Now you see, my dear friend, when the junction will be formed, here you will have donors at the N side, here you will have donors at the N side, and here you will have acceptors at the P side, and this. So dear friend, this would be the depletion region. This is your depletion region. Let us assume that, let us suppose I am making this x-axis. I want to draw the charge density here. So the charge density profile is like this. I used to represent as rho Vx, right? You see, my dear friend, let us suppose xp is the depletion region on the p side and xn is the depletion region on the n side, and w is the total depletion region. This is the total depletion region. So this point coordinate is plus xp and this point's coordinate is minus xn. This is important point. At the p side you have donors. Donors are positive charge and uniformly doped. So here bulk region 0 and here the donor concentration is plus q nt. And acceptors are negative charges, so acceptor concentration is minus q na, where q is magnitude of electron charge and this, right? So this is your profile charge density. This is your charge density. You can write charge density something like this. So I will have rho v as a function of x. This is q nt for the region minus xn to minus xn to 0, and it is minus q na for the region 0 to xp. Okay. If I do the electric field profile at n side, let us see at n side. So at n side I can use a Poisson's equation. So what does Poisson's equation says? d ex dx charge density upon permittivity of semiconductor, epsilon s. I can write this equation as electric field intensity as a function of x. This is rho v as a function of x epsilon x dx. Put the value of rho v at the n side. So electric field intensity, and this portion rho v is q nd upon epsilon s dx, which we can write q nd epsilon s. Integration of dx is x plus some constant c1. I have to calculate the value of c1. It is an integration constant. How can I calculate? At x is equal to minus xn, the electric field must be 0, because at x is equal to minus xn you have bulk n region, right? So I am doing everything from the basic principle so that you can understand how these graphs are you are getting. I am not telling you to memorize, because आपने अगर कुछ memorize किया, let us suppose यूनिफॉर्म डोपिंग होने की बजाय डोपिंग की प्रोफाइल चेंज कर दिया, डोपिंग की प्रोफाइल चेंज कर दिया तो चार्ज डेंसिटी चेंज हो जाएगी, चार्ज डेंसिटी चेंज हो जाएगी तो इलेक्ट्रिक फील्ड इंटेंसिटी चेंज हो जाएगी, पोटेंशियल प्रोफाइल, एवरीथिंग चेंज. सो यू शुड नो फ्रॉम द बेसिक प्रिंसिपल, देन मैथमेटिक्स यू कैन डू इट. इफ डोपिंग इज चेंजिंग, डोपिंग इज डायरेक्टली प्रोपोर्शनल टू rho b, rho b will change, electric field will change, so everything will change. So you think like that. At x is equal to minus action, the electric field should be 0. So we will have 0 is equal to minus q nd epsilon s xn plus c1. So implies that c1 is equal to, उधर चला जाएगा प्लस में हो जाएगा q nd epsilon s xn. Put this value and you will get the electric field intensity. E of x is equal to, you are having this E of x is equal to q nd upon epsilon s. This is x plus xn. This is electric field profile on the n side. Electric field profile on the n side. Electric field profile on n side. Going like this. For the p side, we are having something like this. For the p side, डायरेक्टली यहां से स्टार्ट कर दिए. E of x, p साइड में चार्ज डेंसिटी क्या है, माइनस क्यू एन ए एप्सिलॉन एस dx plus nothing plus, this is the charge density, right? So if you integrate this, this part becomes E of x is equal to minus q n a epsilon s dx का integration x plus some constant c2. How can I calculate the value of c2? You know, there, if I put x is equal to xp, then I will be at the bulk p region, and in the bulk p region it should be neutral. There should not be any electric field. Bulk means neutral. There is no electric field. This basic assumption we do during the derivation. I have told you certain assumptions under which these derivations are done, and one of the assumption is that in bulk p and n region there is no electric field. We are neglecting any kind of electric field. So at x is equal to xp, we are in the bulk p region, and in the bulk p region electric field should be 0. So I am using that condition to get this constant. So if I put this value, this is 0 is equal to minus q na epsilon s xp plus c2. So from this c2 is equal to q na epsilon s xp, right? This is your C2. Once you get this C2, then what is Ex? So E of x is equal to minus q na epsilon s x plus q na epsilon s xp. This is electric field profile on the p side. Electric field profile on the p side. Electric field profile on p side. What one clear observation you can have? This is what? This is y is equal to mx plus c type, where the slope is negative and y-axis intercept is positive. Slope is negative and y-axis intercept is positive. Here you see in this case slope is positive and y-axis intercept is also positive. So draw this line. It is a straight line, and in that straight line what kind of graph you are getting? You are getting some this graph. In the bulk region there is no electric field, then slope is positive and positive intercept, this line, this part, and then slope is negative and positive intercept and slope is negative, and then it is 0. So this kind of curve is your electric field curve. This side is n and this side is p, so it is for the np junction, all right? सो इट्स नॉट पी एन जंक्शन. पी एन जंक्शन के लिए देखो, जब पी साइड लेफ्ट में होगा और एन साइड राइट में होगा तो ये ग्राफ बिलो द 0 पॉइंट आता है, जस्ट इसका मिरर इमेज आता है. बट यहाँ हमने एनपी जंक्शन के लिए सो ये पॉजिटिव में चला गया. आइए सॉल्व जो आपने किया है उस हिसाब से आंसर देख लेते हैं. सो फ्रॉम दिस द आंसर, पी एन जंक्शन के लिए क्लास में मैंने कराया ये है, एनपी जंक्शन के लिए आंसर क्या हो जाएगा, ये हो जाएगा. सो ए इज द राइट आंसर फॉर दिस क्वेश्चन, राइट. हाउ? The every explanation is given here. You please just see in a moment. जल्दी से देख लीजिए. डन। लेट्स डू वन मोर क्वेश्चन, एक क्वेश्चन और करते हैं, एक दो क्वेश्चन और करते हैं। लेट्स डू वन और टू क्वेश्चंस। चलिए आइए एक और क्वेश्चन करते हैं। दिस इज वेरी गुड क्वेश्चन, ये लास्ट क्वेश्चन है, ठीक है। बहुत लंबा सेशन मेरा करने का इरादा नहीं था। हमने कितने क्वेश्चन किए, मैंने 5 या 6 क्वेश्चन का मूड बनाया हुआ था। सो वी डिड हाउ मेनी क्वेश्चंस, क्योंकि इतने ही क्वेश्चन आते हैं इस सब्जेक्ट में, एग्जाम में भी बहुत ज्यादा तो आते नहीं है, 10 नंबर के आसपास आता है। सो वी डिड दिस क्वेश्चन 1, then this 2, and then this 3, this 4, this 5 and this last 6 एक और कर लेते हैं, ठीक है। सो 6 क्वेश्चन करते हैं, चलिए आगे चलते हैं। The following figure shows the capacitance voltage characteristics of two MOS capacitors with different thickness of oxide layers। ये कह रहा है कि दो MOS कैपेसिटर्स हैं जिनमें ऑक्साइड रीजन की थिकनेस डिफरेंट है और उनके लिए ग्राफ बनाया गया। Then he is saying that except the thickness of the oxide layer, all other parameters are identical for the two MOS capacitors. The frequency range at which the CV plots are obtained and the relation between the oxide thickness of 1 and 2 is given. So question बहुत सिंपल है, बहुत इजी है, बट अच्छा है। MOS कैपेसिटर के लिए ग्राफ, CV plot. My dear friend, I have told you 2 types of CV plot in the class, and this question is also MSQ. You have to check 2 options. I told you CV plot at low frequency. This is V and this is C. So at LF अगर हम देखें तो the plot is something like this. This is at low frequency, right? I have told you this point is flat band voltage. If it is ideal, then flat band voltage is 0. I told you this point, these all things we have discussed in the class. This point is threshold voltage. VTH I used to write as threshold voltage. This is threshold voltage. Okay. Before this, you have accumulation mode. Accumulation mode, right? This is accumulation mode. After this, you have this region is your depletion mode. This is depletion mode. And if you go for this point, this is your inversion mode. In the inversion mode, you have 2 points. You are having this strong inversion and you are having this weak inversion, this weak inversion. ठीक है? But this entire graph, it is low frequency. What happens at high frequency? I have told you at high frequency CV plot is something like this, CV. There is no change in accumulation and depletion mode, so they will remain like this. This point is your threshold voltage and this point is your flat band. So before this, you have this constant value and then it will decrease up to this point. And then in the inversion mode, things will change. Actually, when you do rapid switching, the frequency is very high, inversion layer will form, but the inversion charges will not be able to respond to the change. So you will have this kind of inversion layer, inversion region characteristic, right? This is at high frequency, at HF. this point is this is your inversion mode, and this point is your, this region is depletion mode, and as usual this is your accumulation mode, your accumulation mode, right? These three things. Okay, you got the three regions: inversion, accumulation and depletion. All these three reasons you have. Up now if I correlate these two graphs, so with which this is matching? This is matching with the second one. So this characteristic, both of these curves are at HF. So two options will be removed, low frequency options will be removed. Our answer can be either A or it can be C. इन्हीं दोनों में से कुछ हो सकता है. Now I have to tell you कि how the oxide capacitance is required. So you see, this is oxide 1. So for oxide 1 I am saying threshold voltage VTH1, and for oxide 2 I am saying threshold voltage VTH2. From the graph I can observe that the threshold voltage for VTH1 is less than VTH2, where TH1 is with respect to oxide thickness T oxide 1 and TH2 is with respect to oxide thickness T ox 2, right? Now relate this threshold voltage with oxide thickness. So we have threshold voltage VTH. I told you in the class it is flat band voltage plus this 4Q Ne epsilon S. Phi F is your Fermi potential, C oxide plus this 2 phi F. You know all these things, this phi F is nothing but KT by Q ln Na upon Ni, where Na is substrate doping concentration. This is phi F, and then this permittivity of semiconductor. This is accepted doping concentration, that is the doping concentration in the substrate, Q magnitude of electronic charge. Flat band voltage, BFB is flat band voltage. If it is ideal, it can be 0. So focus on this C oxide. C oxide is what? Epsilon oxide upon T oxide. Dear friends, you see, this we have done in several times in the class, but still I am saying, if oxide thickness is increased, then what is going to happen? Oxide capacitance will decrease. We got C oxide and this, if this is increasing, this is decreasing. And if this portion is decreasing, then you see this entire value will increase. It means threshold voltage will increase. So VTS will increase. What I am saying that कि यदि threshold voltage बढ़ा रहे हो तो sorry oxide thickness बढ़ा रहे हो तो threshold voltage बढ़ेगा, right? अब क्वेश्चन में क्या दिया हुआ है कि VTH2 is greater than VTH1. VTH2 is greater than VTH1 from the graph. So it means what? यदि हम ऑक्साइड के पॉइंट ऑफ व्यू से देखें, so T oxide 2 is greater than T oxide 1, or in other words you can say that T oxide 1 is less than T oxide 2. This conclusion we can withdraw, right? So if we are withdrawing this conclusion, then try to see what can be our answer. Our answer can be high frequency and T oxide 1 is less than T oxide 2, that is option C. Right choice for this question is given by option C. तो इस तरह से क्वेश्चन को हैंडल करना है. आप देख लीजिए पूरा दोनों ग्राफ. शेप ऑफ द ग्राफ से आपको पता चल जाएगा कि whether it is low frequency or high frequency. And then threshold voltage ग्राफ से आप देखिए. So oxide 1 के corresponding T oxide 1 के corresponding threshold voltage is less than the T oxide 2. And threshold voltage अगर less है तो threshold voltage का ऑक्साइड की थिकनेस के साथ रिलेशन निकालिए. दैट वी हैव कैलकुलेटेड समथिंग लाइक दिस, एंड दिस रिलेशन ऑफ द threshold voltage with the oxide thickness will give you this result, and finally the option will be answer C. ठीक है. तो यही कुछ क्वेश्चन मैंने आपके लिए डिसाइड किए हुए थे, आपसे डिस्कस करने के लिए डिसाइड किए हुए थे. 5 से 6 क्वेश्चन ही गेट में भी आते हैं और 5 से 6 क्वेश्चन का ही मेरा इरादा था. I'm not in mood to deal all the topics, possible भी नहीं है, ठीक है. बट एक फ्लेवर देने के लिए आपको कि कैसे अप्रोच करें क्वेश्चंस को, सो आपको अभी थ्योरी नहीं डेवलप करना है, अभी डायरेक्टली क्वेश्चन को हिट करना है। इसलिए मैंने कुछ क्वेश्चन लेकर के और आपको करने का एक तरीका बताने का प्रयास किया है। खूब अच्छा पढ़ा है आपने, अगर मुझसे क्लास में पढ़ा होगा तो विश्वास करिए जितना मैंने आपको क्लास में पढ़ाया हुआ है उससे बाहर कुछ भी नहीं पूछा जाएगा। वी हैव डेल्ट ईच एंड एवरीथिंग इन द क्लास, और यदि उससे बाहर कुछ पूछा भी जाएगा तो किसी से नहीं बनेगा। कंपटीशन में उसके लिए कोई खास मैटर, वो बात कुछ ज्यादा मैटर नहीं करेगी, या कुछ लोग बना भी लेंगे तो ठीक है भाई, वो आउट ऑफ द बॉक्स है, कोई फर्क नहीं पड़ा। जितना मैंने कराया है अगर उतना आपने बहुत ऑनेस्टली किया है तो आप विश्वास करिए यू विल गेट द बेस्ट रैंक। जितनी भी आपको जो भी इस एग्जाम से आपकी एक्सपेक्टेशन होगी वो सारी फुलफिल होगी, अगर सारे सब्जेक्ट में आपने उसी तरह से किया होगा जिस तरह से कराया गया। देयर इज नो पॉइंट टू डाउट ऑन योर एबिलिटीज, यू हैव डन अ गुड वर्क, यू हैव डन हार्ड वर्क। सो अभी खुद पर डाउट करके एकदम जब आप कुरुक्षेत्र में खड़े हैं तो उस समय संदेह करके, अपनी क्षमताओं पर संदेह करके, या मन में इधर उधर के देश भर के संदेह करके अपने आप को कम मत आंकिए, ठीक है। आपने अच्छा पढ़ा है, बेहतरीन पढ़ा है, तो जो क्वेश्चंस हैं वो आप कर ले जाएंगे। हमेशा पेपर में इतने क्वेश्चन होते हैं, चाहे जितना डिफिकल्ट पेपर बनेगा, लेकिन अगर 100 मार्क्स का पेपर है तो 40-50 नंबर के क्वेश्चन सिंपल होते हैं, स्ट्रेट फॉरवर्ड होते हैं, वो किए जा सकते हैं। बट फिर भी लोग नहीं कर पाते हैं क्योंकि वो कॉन्फिडेंस लूज कर जाते हैं। एक दो क्वेश्चन डिफिकल्ट मिला तो कॉन्फिडेंस लूज कर गए। आपको एग्जाम को बहुत अच्छे से मैनेज करना है, और वो तभी मैनेज करेंगे जब आपको खुद पर भरोसा रहेगा कि आपने बेहतरीन पढ़ाई की हुई है तो आप मैनेज कर ले जाएंगे, अदरवाइज आप मैनेज नहीं कर पाएंगे। तो आपने बेहतरीन पढ़ाई की हुई है, आजकल वैसे भी ईसी में बहुत ज्यादा कट ऑफ जाती नहीं है, बहुत मॉडरेट रेंज की कट ऑफ रहती है, तो आप अपना बेस्ट करिए और कुछ ना कुछ बेहतरीन एग्जाम में जरूर करेंगे, ठीक है। क्वेश्चंस का कोई एंड नहीं है, मैं 200 500 400 क्वेश्चन करा दूं, उसका भी कोई एंड नहीं है। तो यूट्यूब पर इतना भी नहीं पढ़ना चाहिए कि आपका इंटरेस्ट ही लूज हो जाए इतना क्वेश्चन कर करके। तो थोड़ा सा ग्लिम्स देना था आपको कि कैसे आप कर सकते हैं, इसीलिए मैंने 5-6 क्वेश्चन करा दिए। बस इससे ज्यादा आपको करने की जरूरत यहाँ यूट्यूब पर नहीं है, बट घर में खुद प्रैक्टिस करिए। इस समय टेस्ट दीजिए, खूब अपनी कमियां पता लगाइए, और जो कुछ आप भूल वगैरह रहे हैं उसको याद करने की कोशिश करिए। कुछ नया पढ़ने की कोशिश मत करिए, जो अब तक आपने पढ़ा हुआ है उसे ही रिवाइज करते रहिए, ठीक है। लास्ट मोमेंट है, बहुत अच्छे से पढ़िए, इफेक्टिवली पढ़िए, अपने ऊपर भरोसा रखिए, आप बेहतरीन करेंगे एग्जाम में, ये मुझे आप पर भरोसा है, ठीक है। थैंक यू वेरी मच, गुड लक, ऑल द बेस्ट फॉर योर एग्जामिनेशन, कम विद द फ्लाइंग कलर्स, एंड एग्जामिनेशन के बाद हम लोग मिलेंगे। ऑप्शन ए कोई कह रहा है, नहीं भाई ऑप्शन ए क्यों होगा, थ्रेशोल्ड वोल्टेज ऑफ 2 इज ग्रेटर देन द थ्रेशोल्ड वोल्टेज ऑफ 1, ठीक है। और यहां से आप देखो ऑक्साइड की थिकनेस ज्यादा होगी तो थ्रेशोल्ड वोल्टेज ज्यादा होगा। तो थ्रेशोल्ड वोल्टेज 2 का 1 से ज्यादा है, तो 2 की थिकनेस ज्यादा होगी 1 से, तो उसी को मैंने ऐसे लिख दिया है, Tox1 is less than Tox2, so Tox1 is less than Tox2, we have written like this। so आंसर जो मैंने दिया है वही सही है, किसी ने आंसर चेंज करने के लिए चेंज किया है, उल्टा आंसर दे दिया है। ये सब ऑप्शंस गेट भी बनाएगा आपको कंफ्यूज करने के लिए, कुछ ना कुछ इधर उधर की चीजें करेगा, कंफ्यूज नहीं होना है आपको, ठीक है। चलिए मैं यहीं पर इस सेशन को वाइंड अप करता हूं। थैंक यू वेरी मच, गुड लक फॉर योर एग्जामिनेशन। गेट एग्जाम के दिन हम लोग मिलेंगे, और उस दिन जो भी इस सब्जेक्ट के क्वेश्चन आए रहेंगे उनको डिस्कस किया जाएगा, और जो भी आपका बीच में आपको कोई ज़रूरत पड़ती है तो डिफरेंट टेलीग्राम ग्रुप्स वगैरह पर हैं, वहाँ पर आप कांटेक्ट करने की कोशिश करिए। थैंक यू वेरी मच, ऑल द बेस्ट फॉर द एग्जामिनेशन।